So welcome back to the third session and of this webinar series. And certain part is repetitive, but every day some new people are coming. So just like in the previous two sessions, means so there was an echo from the live streaming, which I stopped now. So the first thing is that means since some people are new, the genesis of this webinar was the current admission session and things like that. Many universities are open for PhD, some people are open for BTech, MTech, and all the academicians and people related to academics are receiving several calls and recommendation letter requests. So we received many questions like whether civil will be better or chemical will be better. I'm getting branch X in college Y and branch Z in college W, which one will be better? But in the discussion, I found that people are not asking about whether it makes sense to do BTech quantum computing. So when I ask people about this, then most students reply, is there a branch like BTech quantum computing? So then I mentioned that IIT Mandi has opened, DTU has, uh, at least we were in the syllabus forming, DTU has also proposed to open from this year. Uh, then many of our students come for recommendation letter that they want to do MTech in quantum computing, MTech in quantum technology abroad, and they want recommendation letter. When I told them, well, there are MTech programs and MS programs in India in the related field, so most were not aware. So then we thought that we'll conduct some activities to make people aware, and all of them may not be the directly potentially who are looking for doing a BTech or MSc or PhD, but they may be in touch with others. Like some of us are teaching in institutes, and then they can tell others that their students that, well, these are the opportunities in India, this can be done, and this branch is growing. So natural questions came that, well, what will happen if I do a BTech or MTech in quantum computing or quantum technology? So from the very first day, we were talking about the opportunities, means what can be done. Means is it only that after BTech or MTech you have to do PhD, or after MSc you have to do PhD, only the academics is the line? The answer is no. The industry is growing, and there are various requirement of the industry, which are which we showcase through certain interaction. So in the very first day, Dr. Anindita Banerjee from CDAC Pune spoke about their activities, what kind of people work there, and she mentioned that some people who have done MTech in quantum technology are have joined different branches of CDAC, not only in Pune, I mean in other branches also. Then in the last week, we asked Professor Subhashish Banerjee from IIT Jodhpur to join, and IIT Jodhpur offer MTech quantum technologies. And in the same day, uh, Jash, Jashkaran Singh from IIT Mandi was also with us. And IIT Mandi has just started a BTech quantum technology course from this year. And they have minor degree as well as MTech by research. So I quickly share a few slides, and I'll not repeat everything I told in the last two sessions because the recording is in any case available if you have missed. But to move on with the discussion, start with, I just share a few slides, but it will be different from what I told. Well, only one slide I will use from the previous one, and then I'll say something and then move to the invited guest of today's discussions, and you can continue interaction in the same spirit as you did in the last two times. Okay, so to begin with, I show the same list which I have shown in past two lectures also. So in JIT, we offer MTech Quantum Technologies, elective to MSc and BTech, uh, MSc and BTech, several electives, and minor degree on quantum technologies. So these are more or less the framework everywhere. And today we'll have Professor Baladitya Shuri with us. And Baladitya, me, Dr. Anindita Banerjee, who spoke in the first day, we were involved in designing different kind of syllabus. And even if you are not doing a BTech in quantum computing or something, you are doing BTech electronics, uh, BTech computer science, you can take minor degree. Many colleges has open. In minor degree, usually you have to take 18 extra credit other than the credit requirement of your degree program. And then at the end of your BTech, you will obtain a minor degree. In MSc, it's primarily elective. But you remember in the last week, we called two people to speak from CDAC, one from CDAC Noida and one from CDAC Delhi, who did MSc in physics, and they were sometime at our group, and immediately after MSc they joined industry and they're doing different kind of quantum algorithm jobs. So even MSc people with a proper MSc physics or MSc applied mathematics degree, if they do sufficient number of elective in the related field, they are also good for absorption in the relevant industry. So then who are the other people who offer MTech? IIT Jodhpur, and in the last time, Professor Subhashish Banerjee talked about their program. IIC Bangalore offer MTech in quantum technology, and today Professor Baladitya Shuri will talk about the genesis where people goes, how useful is this program. TIIT Pune offered MTech in quantum computing, and you remember in the very first day, Professor Dr. Anindita Banerjee told that she has many colleagues, young colleagues who are MTech in quantum computing from DIIT Pune. IISER Pune offer a program, but it's not called MTech, it's called MS in quantum technology. IIIT Allahabad also offered MTech in quantum information technologies. IISST offered MTech in quantum technology. IIT Mandi offered BTech in quantum science and engineering. So about this program, Professor Josh Karan Singh spoke last time, and DTU proposed a BTech. And then in addition, we mentioned that there are four primary vertical in National Quantum Mission: quantum material, quantum sensing, quantum quantum computing, and quantum communication. And there are separate industries. So all these programs are meant to give you an exposure of all these four types, and then MTech allows you to develop expertise, do a project in the related field, and continue as a specialist. But last time someone was asking what will be better for me. I have finished MSc. Should I go for PhD? And as we mentioned that if you are already know that you are clear that you want to do quantum metrology or quantum computing or quantum communication, you can go in that direction and start your PhD. But if you are not clear and you want an idea and then decides, then first do an MTech, get an idea that which one suits you, which one is more attractive for you, and then move to PhD. So I'll not show the syllabus, what we usually teach in these courses. But then, so I told that I'll show you something. So many different things happens in the quantum world, like classical random number generators are not truly random in the sense, although if it is physically originated, it's called true random number generator. You are tossing a coin. If you know that how much pressure you are giving, what is the air drag, etc., you know the outcome by solving Newton's equation of motion. Quantum mechanically, a state remains in superposition and it collapses to one of the possible eigenstates of measurement. So from that, I can introduce a good quality random numbers. And the other beautiful thing is that here we can have unconditionally secure cryptography. So cyber security can be in the peak of it, and there are problems like auction, voting, etc., which are computing problem, but there is a security related to it, and there are several protocols for secure auction, uh, secure voting, etc. So this can reduce corruption. This can introduce strengthen your democracy. So there are many facets, and just since to make a change from what we are doing for the last two. So we just show you some cartoons that, so Alice is in quantum communication, everything happens between Alice and Bob. Alice, and you know about Alice in Wonderland. So here Alice is a girl, Bob is a boy. Bob is asking Alice, Alice, do you know You went to Wonderland, but do you know where is the land where unconditional security is available? So Alice is saying, yes, Bob, it's actually quantum land or quantum world. So if it would become unconditional security, not only cyber security people will be impacted by that, even the police will be impacted. Today, police does a lot of digital forensic, but then they will not be able to do those digital forensic tasks. Now, in quantum communication, not only unconditionally secure communication is possible, there are beautiful things like teleportation, which does not have classical analog. So this cartoon depicts that a man went from Delhi to New York almost simultaneously, and but you see that when by she was teleported, and when he teleported, his nose and ear has been changed. And when he asked the teleportation hostess that what happened, she told that because of the noise, we cannot reach unit fidelity. So fidelity is a measure of how good is a copy. So it's not the copy of the man who entered in New York. So now what happens? As I told that there is a when it interact with the environment, there are measurement happens. All kind of quantum mechanics. So if you do a measure, it collapses to one of the possible state. But even if you don't do measurement, it may interact with the environment and get collapsed, get changed. So controlling noise is a difficult thing. So there are many problems which are engineering problems. We need single photon source, we need quality single photon detectors. There are many problems which involve FPGA board. So electronics engineers have things to do, computer scientists have things to do on algorithm, mathematicians have to do a good job in security analysis. So this is a truly an interdisciplinary domain and everybody can impact. But then further motivation is that what is environment? Suppose you are doing in a particle in a box, except that particle in the box, everything is environment. So here is a cartoon. In an interview, someone asked a participant that why should he recruit you? So he told that I was part of every major quantum computing experiment because I was part of the environment, because everything apart from the main experiment is environment. Then we often tell that the quantum computer is very cool. So your today's generation is familiar to use the word cool everywhere, but quantum computers are really cool. So you see, this is a quantum computer, common picture. But what you see in outside this golden color box, those are not quantum computer. That's a dilution refrigerator that's primarily used for cooling. The actual chip is sitting inside. But there are other quantum computers like you can use. So these are super left hand side top two pictures are of superconducting quantum computer. There can be smaller things like a nucleus, which is used in NMR. So early Indian experiments were with NMR. There can be optical quantum computer. My interest is primarily focused here, and Dr. Henry, who is here today, he is also our partner in National Quantum Mission. We were supposed to build a small photonic quantum computer. The beauty is that that will work in room temperature. Now, many other things happen. So I just take 2-3 minutes and show some cartoons to get you familiar with what kind of things we can do. So here Galileo is throwing a ball in the right. So you are holding the ball by hand, but you can ball. Instead of a ball, you can hold an atom by two lights. It's the same thing. And then you drop the atom. And then we do some kind of interferometry. And what we make is a device which measures the gravitational acceleration g. It's called gravimeter. But from classical gravimeter, accuracy of quantum gravimeter is much higher. It can measure, say, normally you do a problem with g is equal to 9.81 or 9.8 or 10, but it can go up to 9th or 10th digit or 12th digit. Now, that kind of accuracy can help me any change in the surface level. Suppose you go below the round and there is aluminum in one place and iron in another place. So locally, the gravitational acceleration will change at the 10th or 12th digit. So now this is a company which makes this gravimeter, and earlier the prospectors were from Europe going to Africa or India looking for coal, gold, etc. Now you can look at what material is inside and you train your machine where you know the topology below the surface, and then you can check with that this kind of contour plot that what is inside. Now, this sensor can also be used in a hypothetical situation where suppose some people or terrorists have made a tunnel below parliament. So that will change the gravitational acceleration g at a very large, say 12th or 13th decimal place and you can detect it. There can be similar exercise can be done with something called magnetometer. A quantum magnetometer can work with a much accuracy. We can have a handheld NMR device, MRI device, so like a metal detector. So amazing things can happen in quantum sensor. And this has become so popular that even in now the modern cartoon like Marvel Comics is showing that a quantum particle does not exist in any one state, but in all of its possible states at once. So when you do measurement, it collapses, and that's what leads to random number generator. Now, eventually, you can have a quantum cryptography which is unconditionally secure. And here, unconditional secure does not mean unhackable. So hacking strategy are different. You have to use device imperfection. But there is a protocol called device independent quantum key distribution, which is absolutely non-vulnerable, means you have nothing to do. So now CBI is sitting idle. They cannot do anything. So even the policing will change. They have to look for more other kind of evidences like DNA footprints and such things and use human intelligence. They will not be able to crack the communication. So as I mentioned, the photonic quantum computers works in a higher temperature. Other computers are working in low temperature. So this cartoon depicts a takeaway message. Further, it's very exciting and we often work with, even today I post something with the undergraduate students in archive. So this is such a fascinating thing that undergraduate brains works nicely. And this is a list of things which we have done and published with the undergrads. And so I'll not discuss more. I just want you to uh, develop a feel that this is an exciting domain where many things are happening, and this domain is open for everyone. It does not depend on whether you are from computer science, you are from maths, you are from physics, you are from electronics. Everybody can come, learn, enjoy, and contribute. But and to learn and to formally join a program, I show a list of things like BTech and tech possibilities. And every lecture, we introduce some more people for giving you direct interaction. So I'll first request Professor Baladitya Shuri about his experience of running the MTech Quantum Technology program in IISc Bangalore and where the students go, what they learn, and then whatever comes in your mind about you can ask Professor Baladitya Shuri. So Professor Baladitya Shuri is a professor at IISc Bangalore, and apart from one of the leading worker in the domain of quantum technology, he is also interested in science popularization, syllabus formation, etc. And he took very active part in forming the syllabus for minor degree, which now will be offered in many places in India and also in the formation of the syllabus of MTech in quantum technology. So you can ask questions only after he speaks. So over to Professor Baladitya Shuri.
Thank you, Professor Pathak, for the introduction. And sorry for joining a few minutes late. I was stuck in traffic. So, firstly, a very good afternoon to all the participants. I'm Baladitya. I'm a faculty of the Indian Institute of Science in the Department of Instrumentation Applied Physics. My area of core research is I work on both the theoretical and experimental aspects of quantum information processing. On the experimental side, as Anirban said, I work in superconducting quantum computation as of now. And my group is also doing theory work in open quantum systems. And we are also interested in quantum sensing. And we are slowly also developing a line of research in space instrumentation or astro instrumentation. So now I will briefly introduce the circumstances in which our MTech program in IISc was launched, the thought process that went into it, and what the students learn there and what the students are doing after they graduate. And then briefly, I'll talk about the other programs that Anirban mentioned, for which I was involved in the curriculum design. So it was around 2019 when Ministry of Electronics and Information Technology was discussing a project for quantum computing, which involved three institutes: IISc, RRI, and CDAC. And I'm very nice to, it's very nice to hear that a good friend Henry is going to be part of this session. So he's from CDAC, Bangalore. And the three institutes were given a mandate to lay down the initial groundwork for, it's like a initial project. It was the first funded project in quantum computing in that sense, in superconducting qubits. And while discussing that, we immediately realized that we were not getting manpower. So we were given money for manpower, but we almost did not hire anybody because we could not get the people with the right. It was a 3-year project, and to train somebody, it takes a couple years in this field, and then you expect them to deliver and achieve certain goals. That becomes unrealistic within the time scale of the project. So this was when a few of us at IISc gathered. Mainly, it was I and Professor Apurva Patel who led this discussion, and we felt an immediate need for launching an MTech program in quantum computation and in quantum technologies. And this was also the time when the IISc Quantum Technology Initiative took shape on the sort of riding on the wave of the MIghty project. And it was very clear to us that there were quite a few people, around 40 people at that point of time, from almost 11, 12 departments of IISc, cutting across all 6 research divisions, who worked in areas of their core departmental domains, but also intersecting strongly with, they were also addressing quantum problems. And some of us were, of course, working in core quantum technologies as our daily bread and butter. So that was the context in which this IISc Quantum Technology Initiative was formed. And when we started thinking about an MTech program, Professor Patel works in quantum computation, but then we had several people, and I work in quantum computation at that point. That was my only sort of core domain. And but then we had several people who also did quantum communication, like Professor Varun Raghunathan in the CE department. And then there were many, many people, IISc being a traditional stronghold for material science and condensed matter physics. We had a lot of people who worked in quantum materials, and they were, some of them were actually making devices for single photon generation, etc., etc., etc. So we saw a potential for a quantum technologies MTech program, which spanned all 4 verticals, which is quantum computation and simulation, quantum communications, sensing and metrology, as well as materials. So then we prepared the curriculum for this. So the curriculum was designed to, of course, I'm not going into the credit structure and other things of, because those are department and institute specific. But the main structure of the program is it involves hardcore courses, which are compulsory for all incoming students. And then we have a pool of softcore courses. Softcore courses are courses which you can think of them as more advanced and giving you more depth in the core domain and also in related allied domains. And then we have electives, which give the student the freedom to skill themselves in areas which the core program may not be able to address. So this was the broad outline, the framework in which we worked to prepare this curriculum. So in the hardcore pool of courses for the IISc Quantum Technology MTech program, we introduced 4 courses, one each as an introductory course in each of the 4 verticals. So we have an introduction to quantum computing, which for the first couple years of the program until his superannuation, Professor Apurva Patel taught this course. And then there was introduction to quantum measurement and sensing, which is a course I handle. Even today, I teach that course. And then we have introduction to quantum communication and cryptography, which is an intro course, and that is handled by a couple of instructors, including Professor Varun Raghunathan and then Professor Sanjit Chatterjee, who works in the domain of post-quantum cryptography. And then we have a course for quantum materials, which is handled by that course. In fact, because of IISc having a lot of faculty, that course has had a several rounds of instructors taking turns teaching the course. And in the quantum computing course, so these are the 4 core courses and compulsory courses which every student has to take. But then students from, you know, for an MTech program in a place like IISc don't all come with ready-made knowledge for quantum technologies. So we have to also give them the foundations. But then it's also a master's program. A master's program has only a 2-year time frame and a limited number of credits, and every credit has to be put a heavy price on, because it's essentially you're taking valuable time out of a master's program. So every credit has to mean a lot to the student and add value to the student's knowledge. So this was the biggest challenge in designing this curriculum, how to balance the basics while also imparting these courses at a graduate level, because we cannot have the course offered at an undergraduate level, because the purpose of the program or any master's program is it has to prepare the student for both advanced academic research, that is scientific research happening in academic institutes, because there may be students who want to secure a PhD position after the MTech program and then continue research in an academic environment. Or there could be companies who want to recruit trained personnel and employ them directly in R&D roles within their companies. And this is essentially industrial R&D. And we realize that the requirements for industrial R&D and academic R&D are essentially the same. The work environment is different, but the requirements from the people, the human resource, needs to be trained in pretty much the same way. So the program has to, on the one hand, impart all the basics, because students don't come in with the knowledge, but it should also take them to a level where they can dive into industrial R&D or academic R&D positions straight away. And there was no, we thought about this problem a lot. We considered having a semester of quantum mechanics and other courses, but that was just becoming too much for from a credits perspective. And asking the students to take those courses under electives was also not an attractive option. Why? Because usually students want to have freedom to choose electives, which will also skill them in areas beyond the core domain, just in case they need to look for employment in other areas. And this is an increasingly valid scenario. So the program has to be limited to 2 years to teach all the basics and then make the masters at the end of it, give them enough room to take electives, and also impart enough in the core domain. So these are typical challenges involved in designing a master's program. And this is not only for the ISc program, but a highly interdisciplinary master's program at any level, in any institute, be it in India or abroad. And I also want to make a point here that the master's programs that Anirban talked about that are going on in India are truly cutting edge. They actually don't lag even an inch behind any of the master's programs that are happening across the world. As an insider and being part of not just one, but as Anirban said, I have been in discussions with various bodies planning such programs. I think it's a golden time for quantum education in India. And so this was the biggest challenge that we were faced with when we were designing the curriculum. So what we did was so Anirban, how many minutes do I have?
How many minutes you need?
Okay, I will need maybe 3-4 minutes, not
Okay,
more.
okay,
I
please.
I just wanted to give them a peek into the thought process that went into.
Please continue.
Yeah. So this was the challenge before us. So what we decided was we'll have one introductory course in each of these core subjects, which the student necessarily has to take. And then we have a second layer of soft core courses. That's the terminology we use in IISc, but in other places they are also called specialization electives. Specialization electives or softcore courses in IISc are, for example, after the first level of courses, we have a course in advanced quantum computation, which again Professor Patel used to teach. And then there was a course in, like I am offering a course on advanced quantum measurement, topics that are too advanced for the first course, but definitely require, if somebody is interested in that domain. Then there is post quantum cryptography, which usually the communications people take. And then there is quantum information theory, which also the sensing and communication people and also the computation people take. And there is quantum error correction, and there is, and these are all some of the core courses. And then there is a course on 2D materials, because 2D materials in fact are increasingly finding space in quantum materials and devices discussions, not just for fundamental studies where people like Professor Arindam Ghosh and others, they studied the properties of graphene and others over the last 2 decades. But now they're also making devices for single photon generation and detection using these 2D materials. Graphene was an early 2D material, but after that, there is a plethora of 2D materials that have now been discovered and are being researched for various applications in various labs. So all of these courses and many more, in fact, I'm not mentioning many of them, form the second layer of specialization electives. And in addition to uh, the problem still remains, right? And our input is, say, a bunch of computer scientists, electrical engineers, electronics engineers, physics students, math students, chemistry students, mechanical engineers. I'm naming all uh, undergrad backgrounds that have actually joined the IISc MTech program over the last 5 years now. And we need bridge courses. So I offered this course called Foundations of Quantum Technology. And this course was supposed to just give them just the right amount of quantum mechanics in maybe 5, 6 lectures, so that they don't get completely lost, because you can't expect quantum computation course to teach them quantum mechanics, because if every course had to also cover the basics, they would not end up anywhere with the actual material that they plan to teach. So we needed a separate course, and that's the Foundations of Quantum Technologies course, which covers just the right amount of uh, quantum mechanics and some amount of statistical physics to understand quantum materials and quantum computation, the postulates and other things. And then we have some elements of electromagnetic theory. And this course, mind you, is not for some topics are repetitive for the physics background students, and some topics are repetitive for the engineering background students, but that cannot be helped, because when we have a highly interdisciplinary, multidisciplinary class, some students will, a foundational course will have a repetition of material from different backgrounds. So, and then this course also covers elements of group theory and number theory, which find their way in many cryptographic and error correction protocols. Especially cryptography uses a lot of group theory and number theory, and error correction uses a lot of group theory. So we needed to teach the students there. And if you ask them to take, a full 1 semester course in group theory or algebra or something in a maths department, that's recipe for disaster. The language that these students are familiar with and the language that is taught, that course is taught in a maths department, will be very difficult to handle. And then we also, so the foundations course was supposed to be this bridge course to plug the holes or fill the gaps in their knowledge. And then we also needed lab courses. So we have a basic quantum technology lab. And in that lab, so what do we then impart in a lab course at the grad level? Now, in an undergrad lab course, typically people do experiments like Frank Hertz, black body radiation, Compton effect, X-ray diffraction, which are all at some level showing quantum features. So that is one approach we could take. The other approach we could take was, what is the need of the hour? We want these master students to dive into industrial R&D and apply and quantum research in cutting edge frontier labs, which means it's not enough if they do Frank Hertz experiment and Compton effect experiment. They actually need to know the technology that goes into the implementation of quantum hardware. So we decided we were going to take the second route and not worry about actually making them do all these fundamental quantum experiments, but instead train them in advanced electronics like RF electronics, which even electronics communication engineers very often don't study in depth. So we have a curated set of experiments which takes care of that domain. Then we have experiments in the optics domain, starting from the basics of coherent sources detection, square law detectors, all these things. So the quantum technologies lab actually does not have quantum experiments, but it has training. It gives them hands-on training working with all of these hardware platforms, so that by the time they finish this program, they will be knowledgeable in a first-hand way, working with RF systems, say working with a VNA, working with some signal sources, arbitrary waveform generators, scopes at a reasonably high frequency, various RF passive components like attenuators, directional couplers. We have experiments for all of these. The entire RF domain is covered in that course, as well as optics, and we also have simulations. So we have open quantum system simulations using freely available packages like QTIP in Python. And then the students also learn. We give them tasks where they learn and perform them using Qiskit simulators, as well as now we also have our own indigenous simulators like QSIM, which are housed by on CDAC platform. And now we have
Professor Shuri, I think we have to take questions few and then move to Henry also. And so
yes,
please continue.
sure. So this is the overall structure of the program essentially. And what have this in 1 minute, I'll tell you what our students have been doing is our program has been very successful. So we have graduated roughly 50 plus students, with more than 80% of them joining industry, and about 20% of them have secured admissions in various PhD programs. Some of them are doing PhD in IISc itself. And it has been meeting the goals of the program. And what is more heartening to see is the students have joined the core domains. They are not joining, say, software roles after this program. They're actually joining R&D roles in companies like Fujitsu, India Research, and then startups like Axela Quant, and which have hired them for their, and one of our students has also joined CDAC. Yeah. So that is all I had to say, Anirban.
Thank you. It was pretty detailed, and I can see Sushant Goel has raised a hand. So Sushant, you can unmute and ask your question.
Yes.
Good afternoon, sir. It was an amazing description of IISc Bangalore Quantum Technologies course. And I have been to IISc a lot of times when I was in undergrad, like almost 10, 12 years ago. And I was also present in the previous seminar like this. And I did mention like I am really deeply interested into quantum optics. And I have studied a lot about it. Sir, you have told like you have given a very lot of advanced lectures on quantum measurement. So obviously, even I'm deeply interested into it because these are like somewhere plunging deep into fundamentals of quantum mechanics. So,
Correct.
sir, is it possible to get a detailed course list of IISc or MTech program with all the reference books and everything, whatever the hardcore and the soft courses that you have?
Sure. It's actually there on the website. If you go to the IQTI website, we periodically update it, and the course syllabus references, they're all there on the IQTI website under the academic page.
Okay. And
yeah.
Sir, have you recorded any of these advanced quantum measurement lectures on NPTEL or somewhere?
No. I haven't Because see, I joined IISc 8 years back, and I have been teaching this course for 6 years. It takes a certain amount of time for for a course to evolve to a level where either a book comes out or recorded lectures come out. So I will be doing it in the next couple years, but this course has evolved continuously over the last 6 years.
Okay, sir. Thanks a lot. Thanks a lot, sir.
Yeah.
But you want to see a lecture set of lectures, follow Preskill's lectures, means they are.
Yeah. On quantum computation, quantum measurement, that what he was asking, quantum measurement is not a topic that's
No.
often there.
This will be part of the things.
IISc is unique in the sense that we have two quantum measurement courses now, an introductory and an advanced quantum measurement. And the second course also delves into a lot of philosophical aspects, interpretations of quantum mechanics, because they are actually tied to measurement, the measurement
Yes,
problem.
yes.
So, but the first course is very practical. How do you do a quantum non-demolition measurement? How do you design the measurement? It's more about how to practically design a measurement strategy.
Oh, okay.
So
Yeah.
any
Sir, can
other
I ask
question
one
from-
more?
No, just a minute. Means any other question from anyone else? Anyone else wants to ask a questions? Okay, then you can ask your second question, but be very precise.
Yes. Sir, like you told, like there have been a lot of experiments on single photon systems, and I've
Yeah.
just read the theory part of it, and I just know like there are different probability distributions, poison, sub-poison, and superpoison. But how do you claim experimentally that a single photon exists? This thing really
It's an
excites
excellent
me a lot.
question. It's an excellent question, and the way to do this is you do what is called a G2 correlation, a second order correlation measurement. So it's a statistical measurement. So what you do is you have a source and you output I'll give you the very basic sketch of how the experiment would work in any domain. You have a source which is outputting single photons. You pass them through a beam splitter. If they pass through a beam splitter, they come out of one or the other port, but not both. So if you then do a coincidence measurement between the two ports, you should see that simultaneously only one of the ports clicks. So therefore, the simultaneous coincidence is anti-correlated, or rather it goes to zero.
Okay.
So that is the measurement which proves that there is a single photon at the source. So this has to be done. It's a calibration that you have to do.
Okay,
It's very
thank you.
interesting, sir. It's very interesting. Thank you.
Anyone else has any other question? If not, we'll take the questions again at the end and we would move to Dr. Henry. Dr. Henry is associated with CDAC Bangalore campus. So every lecture means in this webinar series, we had somebody from CDAC. But Dr. Henry is in the leading role and he is part of several big projects, including our National Quantum Mission project, where we are supposed to build a photonic quantum computer. He was also involved in developing a very nice tool called Q Inverse. So if you write universe and then you replace U of the universe by Q, and that's an excellent learning and teaching tool. And that has a possibility to get interface with all kind of quantum computer, which have shown that there are NMR-based quantum computer, there are photonic quantum computer. So tomorrow when we'll have our own quantum computers, like what you do with IBM, it can be connected with that. And independent of that, if you want to learn Grover's algorithm, Shor's algorithm, it's an excellent learning tool. But today's purpose is to showcase the opportunities in this field. So all these people who are working in CDAC, in group of Dr. Henry and in other group, they are essentially working in quantum technology, and that exactly tells you that if you do the courses like I told or Baladitya told, means at the end you want to go to, if you are not interested in academia and you want to go to industry, there are positions, and not only that, they do need people, and people need trained people. Nobody has an option to start from scratch, what Professor Shuri was also telling. So there is a requirement of trained people and there are opportunities, but I'll not elaborate. I'll hand it over to Dr. Henry to speak in his own way. And once Dr. Henry finishes, whatever questions comes in your mind, you can ask him. So over to you, Dr. Henry.
Thank you, Professor Anirban, for the nice introduction. Thanks for inviting me on this great opportunity to interact with students here. I lead the quantum technology group in CDAC Bangalore. So we work under various domains in quantum computing, communication. I'm primarily a computer science engineer. I'm not a researcher like Professor Anirban or Professor Suri. I'm from the computer science background, but I understand that there are many scope even for the computer science engineer in the quantum technology. So that is what I am trying to speak today. One of the picture which cartoon that which Anirban Pathak has shown, it was talking about some time travel, yeah, space travel, right? So I will time travel to 1983, right? If I tell about 1983, what comes to your mind? Generally, the India's first World Cup win, right? But there is one technology revolution that happened in 1983. That is nothing but the internet, which was launched. No one knows when the internet was invented, but because it evolved, the technology evolved over the years. But January 1983, when the internet was actually launched. Now let us imagine a professor like a Suri or a Anirban Pathak. In 1983, they walked into a classroom and say that, hey students, look at here, there is a technology called internet, which is going to revolutionize the way we are going to communicate, the way we are going to do commerce, the way we are going to connect with people. Many would have dismissed the idea saying that it's a niche area. Yet many institutes and companies, they adopted internet, right? And they produced many technology leaders and researchers in this decade, for this particular decade, right? But many who stepped back and said that it is a niche, they had to do the catch up. I think quantum technology is exactly in that moment, right? We are talking about a technology that is not fully mature yet. It is still being developed. The rules of this game is being daily written. You can see many researchers coming up with new schemes, new approaches, new innovations in this domain. And I think when these things are happening at this moment, this is the time there is a lot of challenges, engineering challenges in building these systems. And this is where I feel the opportunity exists, right? And this opportunity exists not only in one particular area. Anirban Pathak talked about multiple pillars of quantum technology. So the opportunity exists in all of this technology. And every component that we need to build these quantum systems, right? We import from outside India, right? We don't have the complete supply chain. Say, we wanted to have a superconducting system built. We know that there is a big cryogenic system that is required, dilution refrigerator. We depend on Blue Force, Mabel kind of companies to give us a reliable dilution refrigerator. There are some efforts in India to build this dilution refrigerator, but we still depend on others. Even the wiring, the coaxial cable and the high density wiring that we are speaking about, we depend on some companies like Delft Circuits, which give us this high density wiring, right? And the quantum processor development. Luckily, we have some good professors and researchers who are developing some quantum processors. But again, we need a lot of such researchers who needs to develop these quantum processors. And when I talk about control electronics, the big name comes into our mind is Q-Blocks, Quantum Machines, and then Zurich Instruments. All of these are foreign players, right? We don't have a reliable control electronics being built, right? We don't have it in a very large scale, which can support large number of qubits. So there are a lot of opportunities that exist in this domain. And particularly coming from CDAC, right? And I am being a computer science guy. There is a lot of gaps that we can fill in the area of quantum software development, right? So if you are a computer science guy, you need not worry that you don't understand quantum. Even I don't understand quantum 100%, right? I only understand 10% to be frank. But I know how to build a software that can take these quantum computers to the people. So if you're a computer science student, you can build this quantum software. You can build the quantum middlewares and simulators. You know how to write Python program. It's well and good that you just need to sit with one quantum mechanics guy, and then you need to understand the mathematics and matrix behind that, and you code that in a Python, right? It's simple to develop a quantum simulator. So that's how even I started my career. I started my quantum career with developing a quantum simulator. And I am being a computer science guy. I sat with Professor Anirban Pathak, who was the knowledge behind the QSIM simulator. So he said that I'm going to develop this simulator. I need your support in making that into an ecosystem. So we built a platform called QC Workbench, which is available in qctoolkit.in. So you will be able to develop your quantum circuits there. impose some various quantum noise parameters. So Anirban was talking about various noise that is there in the real quantum systems that you can introduce, and you can run your quantum algorithms on an idealized real quantum systems, right? Real noisy quantum systems. So that's how we started this platform. Then we slowly built a team. Professor Suri talked about the project that we all worked together, CDAC, RRI, and IAC, where IAC was building the 4-qubit superconducting system, and CDAC's mandate was to build a control electronics. So we just hired some of the FPGA guys who know how to write this FPGA programming and burn it into an FPGA cards. So we use them and we built a control electronics for the 4-qubit superconducting system, right? And then we also worked with IIT Madras for building control electronics for the quantum communication, the QKD networks, right? So there are multiple opportunities, and CDAC, particularly being a high performance computing system. So we are called as supercomputing people. We have been deploying supercomputers, and we have deployed around 34 supercomputers across India right now under National Supercomputing Mission. So we always believed that any meaningful application will always require both the HPC resources and the quantum system. So you take any application, let's say you want to develop a new drug, you want to do a reaction modeling in the drug discovery, or you want to develop a new material, you want to do an optimization problem. 90% of these problems are classical. Okay, so we need classical systems to prepare our input. We need to do a pre-processing and post-processing. And we only need 10% of quantum system to solve those problems, right? So we always believe that HPC and quantum, the hybrid HPC quantum, is the future, or the mid-term quantum computers can really be used for, right? We don't only require quantum systems. We need both of them to solve these kind of problems. So that's the reason we decided that we should establish, we already have supercomputers, we should establish a superconducting based quantum system. And thanks to Professor Suri, who was an external expert, who was validating the tender requirements and what are the specifications that should go into an 108 qubit quantum system that CDAC is building right now. So I invite all the participants to visit CDAC Electronic City office. We are right now building the 108 superconducting system, and you will be seeing how difficult, how challenging it is while this system is being built, right? Right now, the installation is done by Rigetti Computing, India. And you will, if you visit now, you'll be able to see how these things are being built, because in the October month, we will be closing the system and it will be operating, right? So interestingly, this system has been co-located with the 30 petaflop supercomputer, which is deployed in the Electronic City office. And we are working on how we can make use of both the computing paradigms to solve some of the meaningful problems, right? So there are opportunities exist, and CDAC is focusing on all of this area, including the photonics lab. So we have a photonics lab where we are trying to build a small scale photonics system along with the support of Professor Anirban and then Professor Chandrasekhar from IAC. So you can come over to our lab, you can have a discussion with us. And the Quniverse platform, which Professor Anirban Pathak was talking about, when I was understanding the potential of quantum systems, when I entered into the world of quantum systems, I was stunned because I saw that there are plenty of modalities exist. There is superconducting system, photonic system, ion trap, neutral atoms, NV centers, NMR, right? There are plenty of modalities. And as an application developer, I'm not really sure which modality will actually solve my problem, right? Rather, I should be worried about solving my problem. So I decided that why not build an unified platform, right? Let it host all of these modalities and let it have a transpiler. What this transpiler does is, let us give one way of writing our problem, one way of representing our problem as a quantum circuit, right? You stick to a gate-based approach, a digital approach where you design your problem as a quantum circuits, and then you run these quantum circuits on various simulators that are available in the market. Let the simulation happen on the high-performance systems, and then you validate your results. And the same code is available for you to run it on superconducting system. And our transpiler knows how to transpile that into an optical circuit that should be run on a photonics system. So this platform, unified platform, was an idea that we came up, and we actually floated a a survey asking whether users really need a such platform. Interestingly, at least 50% of users felt that such a platform is required. So you can visit quniverse.in, and you can create an account for free, and you can explore all the quantum algorithms that you wanted to learn to understand the quantum mechanics and quantum programming, right? So that is one way of learning quantum systems. And CDAC also does some training programs at regular intervals. So we have almost trained some 5,000 to 6,000 users in last 2 years timeline. So you can be part of that program. And CDAC has been recruiting from, even we have recruited from IISc. Last year, we recruited 7 people from MTech in Quantum Technology Group from IISc. So we have a lot of opportunities in CDAC. The moment I am speaking right now, if you go to cdac.in, we need 15 posts in the areas of quantum algorithms and photonics, right? And every 6 months, we post something called just-in-time recruitment. So just-in-time recruitment is every 6 months it happens. You can keep visiting cdac.in, and you will have various opportunities that is posted over there. And we can discuss on various problems that we wanted to work as well. So the point that I want to make is the quantum revolution cannot be built by one type of engineer. It needs to be built by multiple types of engineer, the multidisciplinary people. So whether you are from an electronics domain or a mechanical domain or a computer science domain, you all have a major role to play in changing the way we are going to compute in the future. Thank you so much, sir. If you have any questions, I can answer.
Yes, yes. Thank you, Henry. And this is very positive, encouraging. And though today the number of participants is low, but it's all going in YouTube, and students can see in YouTube and get to know that this is the exciting field, and there are really jobs after completion of degree, and there is a challenging things for everyone. But now it's open for questions. So participants, you have any specific query, you can ask, and you can also ask to both the speakers.
Thank you, Henry, for such a nice motivation behind this quantum computing thing. So I want to ask a question that, yes, naturally, this quantum computing, quantum communication may be the next big revolution. So what are the timelines do you think that this quantum computing or quantum communication will become so big that it will employ large number of people?
So the time is already there. So if you look at, there are many startups supported by National Quantum Mission, and there are many small scale industries that have started up working in quantum systems. So we were talking about these various subcomponents of quantum computing ecosystem, right? Like Professor Anirban was talking about the lasers, detectors that needs to be built indigenously. If you look at that, there are many supply chains that Indian engineers can fill up. So the opportunity is already exist. We can definitely look at developing our own time taggers, for example. Time taggers are finally going to have an FPGA, right? And we have very good FPGA engineers who can build this time tagger. And if I want to buy one time tagger, say the good time tagger, it at least costs 15 lakhs. It's a Swabian time tagger which costs at least 15 lakhs. And we can build these time taggers by our FPGA engineers. So there are many opportunities that already exist. Particularly, we are in the era of noisy quantum systems. We have not really matured. So the technology has to mature. The materials that we use, the components that we build, that still has to mature. So there are a lot of research opportunities here to take these developments to a stage where we will have a fault-tolerant quantum systems. Coming to quantum communication, we can say that the communication is always a matured technology because of the QKD establishments that India has done, particularly professors like Anil Prabhakar from IIT Madras, who is working on establishing a quantum communication network from Chennai to Delhi, almost a 2,000-kilometer thing. And he has, I think yesterday they were demonstrating Chennai to Bangalore link as well, which is connected to CDAC as well. So there are many developments that have already happened. There are many companies started booming up. So the opportunities have already started is what I would be saying. So if you are a student, if you are a researcher, then definitely you have a very good role to play starting from day one. Hope I answer your question.
Yeah, thank you, thank you.
Any other question? Anything specific to the greater than 100 qubit Indian quantum computer?
Yes, Mr. Sushant.
Sir, thanks a lot. And I'm really happy to know like you have got some optical setups also. So in case whenever I come to Bangalore, I have done some work in optics too. I have done, but I'm in teaching in these days now. And I'm also doing a PhD in DFT. But once this PhD gets over, I'll try to get into such kind of things. Sir, I have a question for Professor Suri. I just want to know one thing. Sir, I'm browsing through this your ISC site, and in this quantum technology MTech, all the courses only, sir, name of the courses have been mentioned, but I want
Okay.
the entire list of all the courses, hard course and soft course. I'm not
Okay.
finding it.
Oh, okay. It was there on the website, probably because the new batch is coming and there were some changes in the curriculum. It might still be in production, as in we will be updating it soon. So if you check it after a few weeks, because our classes will start in August, before that, end of July, you should have them there.
Sir, is that will it be available on iqti.isc.ac.in?
Yes, very much.
Fine, sir, I'll recheck up at that time.
Yeah. Because the students use that as their resource to know what the courses are internally within ISC also. They look at that website and then they decide, okay, this is a course of my interest, etc., etc.
Sir, but
People
that
who are not in the quantum tech domain, they do use this as a resource to figure out which course to take.
okay. But sir, if it opens up by August, then fine, I'll keep on checking. But this link would be only available for the students, those who are in ISC, no? For those who are
No, no,
outsiders,
no,
they won't be able to access it.
no. This is a public link. You can any it's a website, so anybody can access it. In fact, the purpose of this website is to advertise, all the activities of IQTI, and one of them is the MTech program.
Oh, okay.
Yeah.
Fine, sir. Then I'll keep on checking every time. Once I find it, fine. Otherwise, I'll just contact
Sure.
you.
Sure.
Okay, sir. Thank you.
Okay.
So is there a question in the chat room? I think. So there is a question in the chat room. How can we correlate the microelectronic circuit, integrated circuit, MSc microelectronics with quantum circuit? Can anyone suggest? Are there
So I
book?
can take this question if you.
Yes, please
Yeah.
continue.
So when you say a quantum circuit, now there are two ways in which you should understand it. So the way an algorithms person understands a quantum circuit is actually in the way you implement it on Qiskit, for example, or you find simple circuit diagrams in books like Nielsen and Schwang. But that is not what you mean when you ask integrated circuits in the sense of electronic circuits. So what you are talking about is a qubit architecture where you have a layout with multiple qubits and their couplers. Unfortunately, there is no textbook yet on this subject, but there are review articles which you can find on arXiv. There is a review article for a quantum engineer's guide for superconducting circuits. So that's a very good review article which will help you understand how these circuits are related, how they are fabricated in technology, using technology very similar to CMOS. So therefore has great intersections with semiconductor processing and VLSI.
Thanks, Baladitya. Any other question? So in chat room, is there any other? No, there is no other question in the chat room also. So somehow today the questions were less, but I feel that the discussion was engaging and many people will be benefited from the recorded version also, which will remain in YouTube and will, just like today we shared in the group, the first 2 days recording the third day's recording will also help, but there may be an impact of sharing that YouTube link today. So as soon as we introduce this YouTube link and people see that they can listen it in their free time, in the third day of the webinar, the participation reduced considerably. So we'll not share it immediately, buddy. Anyway, so I hope it was useful, and then we'll meet again on next Friday at 2 p.m. as before, and this will continue till 10th, and we'll try to engage more people and especially all the people who are offering different courses. And before closing, I want to make a comment that Professor Baladitya Shuri talked primarily about the genesis of the program in IISc, but that started early, and after that, the other programs like DIIT and
Correct.
DIIT and IIT Jodhpur also started. But so when we were designing this MTech program for generally from AICT perspective, the AICT side, everything can be found. Then these were in any case in the background. So this is not the background which is Baladitya told about IISc, not only in the background for the program which is run by IISc. This is the background for the generic structure which is proposed by AICT also. And primary structure is, well, there may be one course which is in semester 3 in IISc, that may be semester 2 in say Jodhpur, and semester 4 in our case. But more or less the broad structure of MTech program is same everywhere, and also the purpose is same. So get ready, and even if you are already doing PhD or you are already teaching, we need a lot of manpower. Encourage your students, encourage colleagues, or people you know and who are interested but does not know much about this area to come and contribute. So thank you all, and we'll close now. We'll rejoin again on next Friday. Thank you all.
Thank you, Anirban.
Thank you, sir.